Okay, so like I said, fluid mechanics is divided into two parts: fluid statics and fluid dynamics. Under the fluid statics, we have hydrostatics and aerostatics, while the fluid dynamics we have what? Hydrodynamics and what? Aerodynamics. Okay, hydro is to liquid. Now, aero there is to what? Is to gases. So our focus today will be on hydrostatics. Hydrostatics. Okay. So hydrostatics simply means liquid at rest. So here our focus is on the properties of liquid that are at rest. So the following are the properties of liquid you should be looking at that can that matter when the liquid at rest. Let me put it that way. Okay, so we have the following. The following are the important properties. Important properties or topics. Let me clean that. It's not neat enough. Properties or topics in fluid mechanics, in fluid statics, in fluid statics. So number one, we have density and relative density and relative density. Number two, you have pressure in fluids. Number three, we have what they call the surface tension. Surface tension. Number four, we have capillarity. Okay, now these are the important topics that have to be treated on the hydrostatics. So my focus today will be on density and relative density. So we have density and relative density. Okay. So, density. Anybody, what do you understand by the word density? Thank you very much. Density of a substance is the mass of a unit volume of that substance. Okay, so in order for this teaching to be easy, let's work with a certain highlight. Highlights. So we have density. Then number two, we have measurement of density. Measurement of density and relative density. So let me hide this here, and relative density. Relative density. Then we should talk about upthrust. After that, speak about the Archimedes principle. Archimedes principle. So next we have the flotation principle. Flotation principle. So after that we can solve some problems related to density and what? Relative density. Okay, so number one, we have density and relative density. And somebody just told me that density is equals to mass over volume, which is correct. So density is what? Mass divided by what? Volume. So you can say it is the mass per unit volume of a substance. Okay, so let me put a perspective to that. Now imagine you have a box that has a length of 1 meter, a breadth of 1 meter, and what? A height of 1 meter. So if I ask you for the volume of this box, can somebody tell me what the volume will be? Thank you very much. Since volume in this case should be length times breadth times height, we should have 1 times 1 times 1. That gives us what? 1 meter cube. So this is called a unit volume. The word unit means 1, right? So when they say a unit volume, this is what they mean by unit volume. This is 1 meter cube. If you place this particular box on a scale balance or on a chemical balance and you happen to measure the weight, so the mass of the object, if the mass of this object, that is if mass, let me write that, if the mass of the object is equals to, let's say, 2 kilogram, if the mass of this box is 2 kilogram, the implication is that the density of that particular object density is going to be 2. So the density is going to be 2 kilogram over what? 1 meter cube. So the density is 2. So what we mean here right now is that this mass of 2 kilogram is definitely serving as the density of that substance. Why? Because the substance we are dealing with right now has a volume of what? 1 meter cube. So density, in other words, is a mass. It's a mass of any substance that has a volume of 1 unit. So density is the mass of a substance that possesses a volume of what? 1 meter cube. So in this case, the unit is going to be kilogram per meter cube. So that's the SI unit of what? Density. But we are not limited to what? Kilogram per meter cube. We can have other unit for density. Okay, so we have unit of density. So we have, since it is a mass, the symbol is a rho. Symbol is denoted rho. This is mass over volume. So the units can then be, if mass is in kilogram, and volume is in meter cube, we have kilogram per meter cube. If mass is in grams and volume is in cm cube, we have what? Gram per cm cube. So we can have several forms which mass can be given as. Okay, if mass is in pound, let's say we have pounder mass. I don't want to say just pound because pound should be the unit for weight and not what? Mass. So but if we want pound to stand for mass, we need to use the word pounder mass. So pounder mass divided by, now the volume could also be in inches per inches cube. So we have inch cube. So we can also have something like what? Feet cube. So these are the various forms we can have the unit of density. But as far as most examination bodies are concerned, the unit of volume is usually kilogram per meter cube, and also what? Gram per centimeter cube. Kilogram per meter cube and gram per centimeter cube. Okay, so there is somebody who wants to join this class. Let me quickly add him up. Hello, are you there? Let me know if you are there. So the commonest unit, like I said, is kilogram per meter cube and gram per what? Centimeter cube for density. So I can see some people wanting to join the class at this moment. I don't think I will allow them again because that would be too much of going forth and back. So we have please note a unit of conversion. 1 gram per centimeter cube is the same thing as what? 1000 kilogram per meter cube. 1 gram per centimeter cube is the same thing as what? 1000 kilogram per meter cube. Some people might be confused that why is that so? Isn't a kilogram expression usually greater than a gram expression? Of course, yes. But if you look at it together, looking at the gram per centimeter cube together with the kilogram per meter cube, you realize that this is true. Okay, in order to explain that, let's try to convert a gram per cm cube to a kilogram per meter cube. So this is like saying 1 gram divided by what? 1 centimeter cube. And you need to know that the word centi is a scientific prefix that means 10 raised to the power of minus 2. So if we want to make this a kilogram, 1000 gram makes 1 kilogram. Yeah, 1000 gram makes 1 kilogram. So it simply means that for this to be a kilogram, is going to be what? 10 raised to the power of minus 3 of what? A kilogram. Kilo means 10 raised by 3. So I've just replaced the gram by 10 raised to the power of minus 3 of a kilogram divided by, like I said, the word centi means 10 raised by minus 2. So we have 10 raised to the power of minus 2 meter all in a cube. So this is going to give us 10 raised to the power of minus 3 kilogram divided by, when you open this bracket, what do you think that will give us? Somebody tell me. Thank you. So we have 10 raised to the power of minus 6. Then we have meter cube. So if you look at 10 raised to the power of minus 3 divided by 10 raised to the minus 6. When you do the law of indices, when you use law of indices to treat that, what do you think we are going to get at the end? Can you check it out? To give us 10 raised to the power what? Thank you very much. So that gives you 10 raised to the power of 3 kilogram per meter cube. So this is a testament that what 1 gram per cm cube is equal to what 1000 kilogram per watt per meter cube. Okay, so we have density of common substances. Though in an exam setting, it is the job of the exam body to supply you the density of the substances you have to work with, but sometimes to make your job easier for you and to make some quick decisions, you need to know the density of substances like water. Okay, water majorly. So density of water is equal to 1000 kilogram per meter cube. This is the maximum density of water, and this happens at what 4 degrees Celsius. If you can still remember the anomalous expansion of water, where water happens to be found contracting during an increase in temperature, and we also find water expanding instead of contracting when there is what an increase in what temperature, or what am I saying? During anomalous expansion of water, if you plot volume against what temperature, this is what you usually have for water. When you increase the temperature from 0 all the way to 4 degrees Celsius, this is what you notice. You notice that what rather than water expanding, it is what contracting. Then on getting to 4 degrees Celsius, it happens to have its what minimum volume. Then what happens after 4 degrees Celsius? You see water expanding. You get that? So this region of water, water behaves like a normal liquid, but in the left hand side region of this graph, water does not behave like a normal liquid. So this is called the anomalous expansion of water. So water happens to have the smallest volume at this particular temperature. But if you plot density against temperature, density rho against temperature, you're going to have the opposite situation. So this is what you have. Since the relationship between density and volume is an inverse relationship, so at 4 degrees Celsius, water happens to have its maximum density. So this maximum density at 4 degrees Celsius is 1000 kilogram per meter cube. So the value we have just quoted as the density of water being 1000 kilogram per meter cube is true at 4 degrees Celsius. So can water have a density greater than 1000 kilogram per meter cube? The answer is supposed to be no. The answer is supposed to be no, because 1000 is the maximum possible density of water. But how can it be possible that we have higher density when we have presence of impurities, some impurities? A very good case is seawater. Seawater contains salt in it, which makes the density of water to be more than 1000. But in the absence of other factors, you have to think density of water to be what 1000 kilogram per meter cube. Okay, let's create some space here. Okay, so aside from water, we have mercury. Density of mercury is about 13,600 kilogram per meter cube. So water 1,000 kilogram per meter cube, and mercury 13,600 kilogram per meter cube. Now, can somebody tell me, since the density of water is 1,000 kilogram per meter cube, what would be this value in gram per cm cube? What would be the value? Anybody? Did you say 10,000? Hmm? Thank you very much. 1 gram per cm cube. So the result is 1 gram per cm cube. Alright, density of mercury, we have it to be approximately 13,600 kilogram per meter cube. Now tell me, what would be the result in gram per cm cube? Thank you very much. 13.6. So all you just have to do is divide by 1,000 based on what we agreed here, that 1 gram per cm cube is equal to 1,000 kilogram per meter cube. So please just remember that. Okay, so we have the next to be relative density. Relative density. Okay, now when you hear the word relative in any settings, you are definitely comparing two things: relative density, relative humidity, relative velocity, relative whatsoever. You are comparing two things. But there are some relative expressions that are ratios. Why some other relative expressions are not ratios? They come with subtraction, like you are subtracting one value from the other. The ones that come in ratios don't have units, like relative density. So relative density, which is symbolized as RD, we can say RD is equals to density of a substance over density. Now this should have just been density of another substance, but because water is readily available, we make use of water as a reference standard, so we use density of water. So it is not wrong to have density of a substance A with respect to density of a substance B as relative density. It is not a wrong thing, because it has to do with comparison, so you can have any comparison. But by default, when they say relative density of a substance, the reference is water. Please take note of that. So RD of the substance is going to be rho, which is the symbol for density of a substance, over rho of what? Water. Alright, another name for relative density is specific gravity. Specific gravity. So, which is symbolized as what? Sg. That's another name for relative density. Please take note of that. So when they say specific gravity, they mean relative density. Now, based on what you have seen here, what should be the unit of relative density? Okay, no unit. Good. That's correct. No unit, because it's a ratio of the same quantity. The quantity we have their unit cancel out to give a zero unit, a no unit. So no unit also implies that it is dimensionless. All right. So we have there is something I didn't talk about. When somebody asks you to find the density of a mixture, density of a mixture. Okay, imagine you have a substance A that has a mass of 3 gram, and what? It has a mass of 3 gram and a volume of, let's say, 10 cm cube. And you have substance B that has a mass of 7 gram and a volume of 20 cm cube. And we then decide to mix substance A and B together into the same container. Substance what? A and B mixed together into the same container. So, it is logical to agree that the mass is going to be 3 plus 7. Do you agree with me? Do you agree? Good. So the mass is going to be 10 gram here. And it's as well logical to say that what? The volume of the mixture is going to be 10 plus 20, making it what? 30 cm cube. Now, A is supposed to have a density rho A. B should have a density rho B. Rho A, which is mass of A over volume of A. The second case, we should have MB over what? Volume of B. Now, it would be illogical to say that what? Density of the mixture equals to sum of the density. Hope you know that. You cannot just say density of the mixture is equals to sum of the density of what? The densities of A and B. So what you are expected to do here is to just simply say mass of the mixture over what? Volume of what? Of the mixture. So in this case, it will just be the 10 gram over what? Over the 30 cm cube. So that gives us 1 over what? 3 gram per cm cube. Okay. Please, I want you to off your mic. Okay. So this is how to find the density of a mixture. So don't fall for a trap of thinking that you can add what? The density of two substances together. To pass the message across properly, let me give a quiz. Quiz 1. Substance substance X of density 0.8 gram per cm cube as a mass of 8 gram, while substance B with a density of 0.7 gram per cm cube as a volume of 10 cm cube. Determine the density of the mixture of A and B. So the question is asking you to find the density of the mixture of A and B. Now, if this happens to be a multiple choice question, expect to see something that will be like this, like an addition of what? This and this, which should have given you something like 1.5. Now, the answer can never be that. You cannot add up densities together. So it's important you know that to find the density of a mixture, you need the mass of the mixture and the volume of the mixture. So density of the mixture should be mass of a mixture divided by what? The volume of the mixture. With somebody, should I give you room to attempt it? Okay, I'll give you room to attempt it. I'll give you like a minute to attempt it. I'll wait for your response. Okay, 10 seconds gone. Twenty seconds. 30 seconds. 40 seconds. 50 seconds. Time up. Okay, so the question is asking you to find the density of, okay, you got 0.75. Okay, let me keep that here. Moise got 0.75 gram per cm cube. Okay, let's check it out. Mass of the mixture is expected to be mass of A plus what? Mass of B. Volume of the mixture is expected to be volume of A plus what? Volume of B. We have mass of A, but we do not have mass of B. Mass of A is known as 8 gram. Mass of B, we don't know it, but we have volume and density of A. From density equals to mass over volume, we can get an expression for mass there in terms of density as density times what? Volume. Then divided by, we do not have volume of A, but we have density and the mass of A. So from density being mass over volume, we can get an expression for volume, which is mass over density. So we have MA over what? Density of A. Then plus, we have what? The volume of what? B. Sorry, that should be, okay, that's correct. So we have volume of B. These that I wrote as rho A and VA should have been what? Rho B and VB. So from there we can insert in the values. Okay, let's do that. Let's create room for this. So according to what we have here, they give us the mass of A. Mass of A is given. Let me create room. Mass of A is given as 8 grams. Density of A is given as 0.8 gram per cm cube. Okay, volume of A, density of B is given as 0.7 gram per watt cm cube. Volume of A was not supplied. Volume of B supplied as 10 gram per cm cube. Mass of what? B, we don't know. So we can just go ahead and get the density of our mixture. I'm trying to create some space here. Okay, so you have density of the mixture following what I've written here. You can just say mass of A is 8 gram plus density of B is 0.7, then times what? 10 divided by volume of A is mass of A, which is 8, divided by what? The density of A, which is what? 0.8, then plus volume of B is given as what? 10. So on top you have 8 plus what? 7, divided by, you have 10 plus 10. So what do you have there? 15 divided by 20. So what's that gonna be? So that gives you 0.75, which is correct. It gave us the correct answer. That's Moise got it right. So which means the density of the mixture there is going to be 0.75. Alright, moving on. So recall, let's call these other formulae of relative densities. The general formula of relative density is what I described it as in our last here. I said relative density of a substance is density of the substance divided by what? Density of water. So which means the RD of a substance, any kind of substance, be it solid, liquid or gas, can always be density of the substance over density of water. Okay, number 2. RD of a substance can be seen as mass of the substance over, now take note of what I'm about to write, mass of, now watch, I'm putting this in capital letters so that it will be very emphatic, equal volume of water. Now you'll watch here that I did not just say mass of water, I had to put the statement equal volume, because the absence of that statement will make that formula invalid. It can't just be mass of a substance over mass of water. It has to be mass of a substance over mass of equal volume of water. How do we justify that? From RD being Density of a substance over density of water. Density is mass over volume, so you could say mass of a substance over volume of a substance divided by mass of water over volume of water. This is what I've just written here, and this is what I've just written here. This becomes mass of a substance over volume of a substance times volume of water over what? Mass of water. Now, these two volumes here can only cancel out on one condition, if they are equal. So we have to say that if volume are equal, that is V of the substance equals to V of water, this will cancel out. We'll end up with having mass of a substance over mass of water. So you can see why it is necessary for you to put in what? Equal volume. Alright, number 3. We have other shortcut formula for relative density. Relative density of a solid substance could be seen as weight of the substance in air over upthrust of the substance in water. So weight of the substance in air is W subscript A. Upthrust in water means weight in air minus weight in water. So this formula here is only valid for a solid substance. You get to understand it more after Archimedes principle and flotation principle. Relative density of a liquid substance. This formula is only valid for liquid substances. So this could be upthrust in the liquid, upthrust of a substance in the liquid over upthrust of the same substance in water. Since upthrust is weight in air minus weight in the liquid, so this will be weight in air minus weight in liquid over, we have weight in air minus weight of the same substance in water. So these two formulae are quick formula for determining relative density of a substance, either liquid or what, or solid. You have alternatives of not using this formulae by trying to use the flotation principle and the Archimedes principle, but these formulae are very fast when you are solving problems on multiple choice. Then moving on. Let me give you examples. Okay. 1. A body weighs 20 Newton in water, 30 Newton in a liquid X, and 40 Newton in air. Determine the relative density of Roman figure 1. The body Roman figure 2, liquid X. So the question is asking you to find the relative density of the body and liquid X. So the shortcut here is to use that formula. RD of a solid substance is equals to weight in air over upthrust in water. This is exactly what you have here. So which means we can say the weight in air here is we can write it as WA over WA minus WW. W subscript A there means weight in air, and WW there implies what? Weight in water. So in this problem here, the weight in air is given as 40 newtons. That's what you can see here. Weight in water is given as 20 newtons, and weight in a liquid X is given as 30 newtons. So this is supposed to be weight in air over weight in air minus weight in water. So this becomes, what's weight in air? 40 divided by 40 minus weight in water is given as 20, so this gives us 40 over 20. This is going to be 2, so the relative density there is 2. Then for the second question, it's asking you to find the relative density of liquid X itself. Now let's create room for that. So we have liquid X. The RD of a liquid is meant to be upthrust of the substance in the liquid over upthrust of the substance in water. So that becomes weight in air minus weight in water, in the liquid, over weight in air minus weight in water. This is going to be weight in air 40, weight in the liquid X is 30 over weight in air 40, weight in water 20. This gives 10 over 20. That gives us what? 0.5. So the relative density of the liquid is 0.5, while the relative density of the solid is what we calculated above as what? As 2.0. Okay. Is there any question you would like to ask there? Anybody? Any question? Anybody? Okay. No question. Then we can move on. All right. So I need you to solve this. A liquid X, okay, a liquid X of density 900 kilogram per meter cube, and water of density 1000 kilogram per meter cube are mixed together. But they remained immiscible. Which of the liquids stays on top? Option A, liquid X. Option B, water. Option C, cannot be decided. So answer that question. Which of the liquid stays on top? And tell me why you think the liquid will stay on top. I'm listening. Okay, why do you think so? Okay, it is correct that what liquid X will stay on top, and you have explained it that what it is because it has a lower density. That's correct. Okay, so we explaining it with mass is partially correct. I don't want to use completely correct because density is not only dependent on mass, it can only be proportional to mass in that case, provided the volume is what constant, if you fix the volume of the substances. Okay, so you're correct. The answer is liquid X. So liquid X has a lower density. Liquid S has a lower density than water. So it floats on water. Okay, so there are conditions for which objects with a higher density can stay on top. For instance, a ship is made of steel, and steel has what densities that are far more than that of water, but the ship still stay on water. What explains that in that case is not density, but what the principle of flotation. We are getting there. Question 3. We have an object. Okay, for that, yeah, a substance X weighs 30 gram in air, 20 gram in liquid Y, and 25 gram in water. 1. Determine the density of X in gram per dm cube, per cm cube. 2. Density of Y in gram per cm cube. 3. Which is denser between liquid Y and water? Would you like to attempt that? Okay, I'll give you like a minute to give me the first answer. Do we have an answer? Okay. 6 gram per cm cube. Okay, let's find out. Let's find out. The question says you have substance what? X weighs 30 gram in air, 20 gram in liquid Y, and 25 gram in water. Okay, let's find out. So we are looking for the density of X. Now you can use the first formula I gave to you to find RD. Now see this. Recall that RD of X should be weight in air over weight in air minus weight in water. The what they gave you are masses, but don't mind here because you don't need to convert it to newtons because this is a ratio of weights, so it can also be replaced by ratio of masses. So we have weight in air 30 grams, so I have 30 gram minus 30 gram minus weight in water is 25 grams, so that gives 30 gram over 5 grams. That gives us 6.0. Now the relative density is 6.0. So note, you know that RD of a substance is density of the substance over density of water. So which means RD of a substance, density of a substance is RD times what? Density of water. So RD here times density of water is 1 gram per cm cube. So this to tell you that RD of a substance is always, density of a substance will always be equals to the RD of the substance if you express it in gram per dm cube. So RD of X is now going to be equals, density of X is now going to be 6.0 times 1 gram per cm cube. So it's correct. The answer is what? 6 gram per cm cube. So that's the density of the substance. Now let's get the density of the liquid X. Or is anybody who has done that? What do you think that is? So you can use that same formula, but now you are using the one for what? Liquid. So that will be upthrust in the liquid over what? Upthrust in air. Upthrust in the liquid over upthrust in water. So RD of the liquid should be upthrust in the liquid, which is weight in air, minus weight in the liquid, divided by what? Upthrust in water, weight in air, minus weight in water. Weight in air is 30 gram. In the liquid is 20 gram. Air, 30 gram. In water, 25 gram. That's 10 gram over 5 gram. So that gives us what? 2.0. Therefore, the density of the liquid will also be what? 2.0 gram per cm cube. And the third question is asking you which of the density, which is the denser, which is denser. This is supposed to be denser. Which is denser between liquid Y and water. Okay, we found the density of liquid Y. Liquid Y, density of Y is 2.0 gram per cm cube. Density of water that we know is 1.0 gram per cm cube. So we have Y is denser than water. So this is what you have for the density of Y versus the density of water. So that takes us to the next stage. So we have methods for determining relative density. Methods for determining relative density. I'll list them. Number one is using what they call the RD bottle. Number two, we have using the U-tube. 3, using a device called the what as apparatus. Number 4, using hydrometer. Number 5, using a lever balance. So these are the various methods used for determining the RD of a substance, and the fastest to use is the hydrometer. So hydrometer is used for determining the relative density of a liquid. Most of the time we use it for liquids. It's just a simple device which you decide to what? Insert. You immerse it in a liquid. So it is it functions with respect to how far it can go when you immerse it in a liquid, meaning in a denser liquid the depth is always very low, but in a liquid that has a lower density it goes deeper in it. Okay, so we have the RD bottle. Let me start with the RD bottle. So we have RD bottle. So if this happens to be the RD bottle, forgive my diagram. Okay, so you have this to be the cork. Then inside here we fill it with what? A liquid, and you cover it with the cork. Alright, so what do? The first step here is to measure the empty bottle. Mass of empty bottle, let's call it MB. So the next thing you want to do is you want to fill the container. Now empty bottle means there is nothing inside here. So the next thing, after measuring the mass of the empty bottle, you want to fill the container with, let's say, liquid X. You measure the mass of what? Let's call mass of the bottle, let's call it M1. You then measure the mass of the bottle plus what? Mass of what? Liquid X. Let's call that what? M2. So the next thing you want to do is you want to pour out liquid X and replace what? Liquid X with what? Water. So what you now have inside there is water. You measure the mass of the bottle plus mass of the water. Let's call that M3. So this will then mean that mass of X is going to be M2 minus mass of, when you take this to the other side, mass of the bottle, which is M1, and mass of the liquid, of the water, is going to be M3 minus what? Mass of the bottle. So this is M2 minus M1. This is M3 minus M1. So one thing you need to know is that what is guaranteed in using RD bottle is that we are going to be using the same volume. Since everything was filled to the brim when you use liquid X versus when you use what? Water, the implication is that they have the same volume. And you can recall I said relative density can be mass of a substance over mass of equal volume of water. So which means that we can say our RD here, which is a mass of the substance over mass of what? Equal volume of water, can be equals to the substance is X, M2 minus M1, over the water is M3 minus M1. To pass the message across properly there, let me give you a quiz. A RD bottle weighs 20 grams. When filled with water, it weighs 35 grams. When filled with liquid X, it weighs 30 grams. What is the relative density of liquid X? So I want you to attempt that using the logic I just explained that. So solve that, please. I'll give a minute for that. Okay, time up. Time up. So following what you have the mass of the empty bottle as 20 grams. They said when the bottle was filled with water, it weighs 35 grams. So which means mass of the water in there should be 35 grams minus 20. That gives you 15. And they said when filled with liquid X, it weighs 30 grams. If you subtract 20 from 30, that gives you 10. They're asking you the RD of liquid X. So we say RD of liquid X should be mass of liquid X over mass of equal volume of water. So mass of liquid X, based on the question, the bottle weighs 30 grams when filled with liquid X. So that will be 30 grams minus 20 grams. Don't forget that 30 grams is not just mass of X, it's the mass of X and the bottle. Then, according to the question, the bottle weighs 35 grams when filled with water. So this will be what? 35 grams minus 20 grams. So on top we have 10 grams divided by what? 15 grams. 5 can go. That gives us 2 divided by 3. So the answer is 2 divided by 3, or 0.667. That's what you have as the relative density of what? Liquid X. So the question is that simple. Okay. Alright. So the next we have the RD bottle. Sorry, I've just explained the RD bottle. So the next should be, let me explain hydrometer. Hydrometer is a device you use for measuring the relative density of a liquid. It works based on the principle of flotation. Okay, imagine you have 2 containers. You have the same liquid. No, let me do it this way. We have a container of a certain size, and exactly the same container was used elsewhere. So let's duplicate that so that we can have regularity. Okay, now in the first container we have a liquid Now to the same depth, both of them have liquid to the same depth. So this is a liquid here, let's call this X. Then here we have liquid, another liquid, let's call it Y. So hydrometer was the same hydrometer was dipped inside the two liquids. Let's duplicate this. Okay, now we have same hydrometer was inserted, into what? The two liquids. So let me draw the hydrometer here for ease. Okay, so here we have a hydrometer. Okay, just hold on. We have this was inside X to this depth, and this was inside Y to this depth. The same kind of hydrometer, this is in X and this is in Y. Now I want you to use simple logic, based on simple logic, to tell me which of the two liquid you think is denser based on what you can imagine. Somebody look at it. Which of the two liquids do you think is denser? I want you to be logical about it. Okay, Moise Y. Okay, Moise said Y. Any other person? Any other person? Tell me. Come on. I need another person to respond. Moise is not the only logical person here. Any other person? Okay. Ella thinks that's what X is denser. Any other person? Fortune Delight, what do you think? Which one do you think is denser between X and Y based on what you can see? Okay, in order not to waste time, let's move on. Now, Moise is correct. Moise is correct. Y is denser. Okay, please, I want you to off your mic. There is a background noise there. Okay, X is denser. This is denser. Now, you can see that. Try and imagine dipping things inside what? Denser liquid compared to dipping things inside what? Liquids that are not as dense. You realize that the objects you are immersing into the denser liquid, we experience more resistance, let's put it that way. We experience more resistance compared to when you are trying to immerse it in a substance that is less dense. So Y is going to be what? Denser than what? Than X. Sure you understand that. Liquid Y is denser than liquid X. Okay, so we have it at what? If H is equals to the depth and rho equals to density of liquid, so you should know that what? The depth is inversely proportional to the what? The density is inversely proportional to the depth. I hope you understand that. Or let's put it this way, it's still the same thing, but I want to write it in a different form. the depth is inversely proportional to the density of the liquid. The more the density of the liquid, the lesser the depth, and vice versa. So which means that if we write something like constant k over rho, we end up having k to be equals to h rho. So I can say h1 rho 1 equals to what? h2 rho what? Rho 2. Okay, now let's create a question here using this particular analogy. Okay, say we have this same scenario, and the question supplies you the density of x to be 0.8 gram per cm cube, and supply the density of y to be 0.9 gram per cm cube. And the question gave you the depth here in y, maybe the question gave it as 18 centimeter. So the question is not asking you to find the depth of the hydrometer in this, let's call this y. The question is telling you to find y. Find y. Now to find y, you have to use the logic here, what I gave here. But yeah, I want you to do that now and get me the value for y. What did you get? Twenty more seconds. That is correct. The answer is what? 16 centimeter. Okay, so you use h1 rho 1 equals to h2 rho 2. So you are looking for h2. h2 there should be what? h1 rho 1 over what? Over rho 2. So our h2 now is going to be, h1 is 18 centimeter times the density there is 0.8 for the first, divided by, we have 0.9. So that gives you 16 centimeter. So you can see that the depth is definitely smaller in y compared to what? How it was in x, because y happens to be denser than what? Than x. Please take note of that. That is how hydrometer works. We use hydrometer for determining the density of a liquid by just what? Immersing it in the liquid and allowing it to float in the liquid. So it works based on the principle of flotation. Please take note of that. Okay, we also have what they call the U-tube. U-tube is used for immiscible liquid. So if you have something like this, this is a tube that forms the shape of a U. So the first thing you want to do is to pour the liquid inside. You pour a certain liquid inside, for instance water. So the water will be inside the U-tube in this manner. So the next thing you want to do is pour the second liquid, for instance liquid X. When you pour it through this route, it's going to push this down and push this up, so you end up having something like this. Let me create room for that. Okay, so you end up having something like this. Let me take this off. So what I was saying is, by the time you pour a second liquid, the left, let's say you are pouring from the left arm goes down, the right arm goes up. So the second liquid you poured into it is probably here. So if we call this the datum level, so we are going to have this part here as H1, this part here as what? H2. So because of time, we may not be able to. Now the pressure at this side is equal to the pressure at this side. They balance themselves up. So you will end up having something like pressure itself is H rho G. So we end up having something like what? H1 rho 1 G equals to H2 rho 2 G. The G will cancel out. We end up with what? H1 rho 1 equals to H2 rho 2, which is also similar to the formula we just made use of for the hydrometer calculation. So like I said, this is used for immiscible liquids that cannot mix together on contact. But if the liquid can mix together on contact, you have to use what they call the S apparatus. S apparatus. This is used for miscible liquids. So if the liquids can mix on contact, so in that case you have to use a device that will not allow the liquid to mix in that case. So you have something that looks like an inverted what? An inverted U-tube. Okay, let's manage this. Let's manage it this way. Okay, something that looks like an inverted U-tube. So this part here, you have a tap. Then here you have a container of one liquid. This side you have another container of the other liquid. So we have liquid 1 inside here, and here we have what? Liquid what? 2. So what do? You open the tap and suck out what? Suck out air in this direction. When you suck out air, what you will successfully do is it will drag what? The liquid along. So we are going to have something here, and it will also drag this along. You'll have different height, H1 and H2. So you can also use the formula H1 rho 1 equals to what? H2 rho 2 here. Right. Now, because of the time, I will be ending the class here today. In our next class, in our next online class, I will pick it exactly from here, and we are going to solve more questions on fluid statics, on hydrostatics. But before I move on, is there any question you want to ask? Okay, if there is no question, we'll end the class here today. And if there is any error in the computation, please let me know. Right. Once again, this is a BMI tutorial. Always what? Reach us via the contact on the board. Bye. Take care.